speaking of relevant and practical, heat exchangers. So this is what we'll be talking about next. Heat exchangers are basically devices that accomplish the task of moving heat from one fluid to another fluid. So they're designed specifically to get heat out of something and put it into something else. There's, I guess, two different large classifications of heat exchangers. One is called direct transfer. So in a direct transfer heat exchanger, heat is exchanged directly between two fluids through an impermeable wall. I guess you could also claim that maybe injecting steam into a fluid is sort of like a heat exchanger, but normally when we talk about heat exchangers, we're talking about things that are contained, have fluid contained on either side of some containment material. For direct transfer, the idea is that you've got heat. It goes directly from one fluid through some resistance into another fluid. That's opposed to indirect heat transfer heat exchangers, where heat is transferred to a secondary medium. That medium is then put in a different flow environment, and that heat is extracted back out. So for example, in HVAC applications, let's say you've got air that's coming out of a building and you want to regenerate that as it comes back in, or you want to take advantage of the fact that air in here is at 80 degrees, or hopefully not 80 degrees, 75. It goes outside, and outside it's at 30, and you don't want to heat all the way up from 30 to 75. You want to heat from, say, 60 to 75. So you put a heat exchanger in the transfer line, and you get this advantage. So you don't actually have any direct contact between the outgoing and the incoming, but you have this big, say, wheel of media, and that wheel rotates. So it goes through the exit stream, gets warm, and it rotates back into the inlet stream, and it gets cold, and so you get this kind of heat transfer that happens. So this is, it's called a regenerator usually. This is one, I guess it's not something that in lecture we're going to talk a whole lot about. There is in the homework problem a reference to a regenerator. It's sort of secondary and unimportant, but it's the same idea. You're kind of taking advantage of the thermal capacitance of a medium as part of the heat exchanger design. So let's talk through maybe some examples of heat exchangers, just because they're ubiquitous. They're something that you're going to see everywhere, and it's good to understand the different types and classifications. All right, so configuration. So we have the classification, indirect and direct. Let's talk now just about the direct heat exchangers. So within direct heat exchangers, there's these different configurations. And by configuration, I mean, let's think about the different ways that fluid could be routed through a device. So there's something called parallel flow. So in parallel flow, what you have is you have cold fluid coming into a pipe, you have hot fluid coming into a pipe, and they both enter on, say, the same side of the flow axis. And then they both flow in parallel to each other and then exit. So that can achieve heat transfer, right? That's a heat exchanger. The characteristics for this are you have hot flow coming in, you have cold flow coming in here. They're at these two different temperatures, obviously. And what's going to happen is initially there's a very large temperature difference. So initially there's a lot of heat transfer from hot to cold. As you move along in position, you start to have a reduction in the delta T locally between the two flows. So the heat transfer rate goes down. So even though the mass flow rate in here and the specific heat is the same, it's not really changing throughout. You have this changing heat transfer as a function of position. And eventually by the time you get to the outlet, there's barely any heat transfer because there's such a small temperature difference. Okay, so that's parallel flow. A second example would be counterflow. So counterflow is where you flip things around. You have hot coming in on the exit side of the cold fluid. So now they're sort of crossing paths like this. In this case, now you get this linear profile, usually, roughly linear profile, where the cold goes up, the hot goes down. I guess one thing that's kind of interesting here is the best that I could ever do with this, if I made this infinitely long, right? The best I could ever do is get TH equals TC at the outlet. I could never get TH equals to TC in unless this flow rate was essentially 0, and this was like very large. Over here, I can cross over, right? Because you're matching at the outlet, and at the inlet, you get this kind of crossover of the temperature. So TC out can exceed like TH out, right? They don't converge to each other. So in most situations, unless there's some reason why you don't actually want all the heat to transfer or something like that, in most situations, counterflow is better than parallel flow. Just because it can achieve more heat transfer for the same amount of material, the same device. Okay, so there's other kinds. There's crossflow. There's shell and tube. We'll talk about those next. So I have some pictures. These are different types of heat exchangers. If you kind of do the performance analysis on, let's say, a tube-in-tube heat exchanger, which is what I was showing in the last one, those actually kind of suck. Like, they're not very good. And the reason is that metal's a really good conductor, usually, compared to the fluids that are going through it. Fluids are typically not very dense. They don't have high conductivity. So if you're trying to get good heat transfer, the limiting thing there is the amount of surface area that's available for convection. So what heat exchangers will typically do is they will add a ton of surface area to take advantage of the fact that heat conducts really well through the metal, can spread out, and then have more surface area available for convection. So you're driving down the resistance on the convection side. So now you look at these heat exchangers and you kind of see what's happening. So you have flow. Let's say this is a header down here, I guess. Flow's coming in. This way, it's probably leaving in the back through another port. And then there's tubes that go up and down, and then there's all these fins that connect it. So this particular device probably has maybe air or some gas that's flowing this way through it. And then in crossflow, you have these, whatever's contained in here, maybe it's a refrigerant or whatever. So that's taking advantage of these fins, essentially, to increase the heat transfer area, and it's a more effective heat exchanger. All right, so this is probably a crossflow, sort of fin-typed heat exchanger. This is called a plate and shell heat exchanger. So in a plate and shell heat exchanger, you just achieve the same thing by adding all these plates on top of each other. All these plates then have flow that goes like crossflow. You have these ports that come in with these like gaskets and channels cut out. And you can like increase the area that you need for these by just adding more plates. So you unscrew the bolts, add in more plates, and you get a more effective heat exchanger. So these are really common for a lot of applications. But again, it's the same thing. You're just trying to increase the surface area. What you'll notice with these is that there's probably a lot higher pressure drop than just tube and tube. Like you've got these tiny little channels. The flow has to like weave its way through these, so there's a lot of pressure drop there. But that's always the trade-off. Let's see, maybe one more little slide of these. So these are really common. These are, if you go look at your air conditioner or the unit inside your furnace, it's going to look something like this. So what this is a cross-flow heat exchanger where you have the refrigerant or whatever it is going through these tubes, contain high pressure. Then you have air that's sort of forced across. So that configuration of having not counterflow and not parallel flow, but actually flow that's coming across has a different thermal performance, which we'll talk about on the next slide. But you see these all the time when there's something like a relatively non-dense gas, like air, at ambient pressure that's being forced through something that has like a fluid on the other side. So this type of thing is really common. And here it's like, okay, you're not going to get quite the performance of the counterflow heat exchanger, but it still does maybe well enough for whatever you want. Okay, so let's look at the performance of some of these. Okay, performance, there's some implications for understanding the performance. So this is cross-flow heat exchanger. Cross-flow heat exchanger, you have fluid coming this way and fluid crossing the tubes the other way. There's maybe different sub-classifications here too. And that is looking at whether the fluid in each of these cases are what we call mixed or unmixed. So, okay, up here we have fluid 1. So fluid 1 coming in is unmixed, meaning I have these like vertical baffles, and those vertical baffles are preventing fluid from mixing along the axis of this second fluid here. So if you have that, you have some temperature that develops in a channel. That temperature can't equalize as you're going through. And what you end up with is, let's see over here. So what you end up with is this kind of inlet profile here, which is a constant temperature, is going to kind of decay. And then over here, you get this, like, the channels that are on the very hot side, those get really hot. The channels that are on the cold side, those don't get quite as hot. So on this side, you end up with this gradient here. So compare that then to like the case where you have mixed fluids, or this one is mixed. So here you still have tubes, that's unmixed. Now you allow this fluid to mix. So this fluid, let's say, is mixing perfectly in this direction as it's flowing through. So you say like uniform temperature in this fluid as a function of this position. Honestly, like, obviously that's not 100% accurate, but it's an approximation, and it gives us a bounding case. So if we look at that, now you look at the outlet here. So this is the mixed fluid coming in, right? This stuff up here. So this is the mixed fluid coming in. It's coming in at constant temperature. It's leaving at constant temperature up here. So that's a very different profile from up here where it's not constant. So it just means that when you're going through the analysis, you have to like think about this, and the correlations or the performance equations are going to be different for each of these different cases. Okay. Good. One more. Okay, I know I've been talking a lot here, but heat exchangers are so much fun. So one more that you see often is something in power generation, any place where you have like really high pressures. This is counter crossflow. So this has, let me just draw on it. So in this case, you have, let's say, one fluid coming in here. You have another fluid coming in here. So some in the classroom might be familiar with molten salt to steam heat exchangers. This is used for concentrating solar technology. Looks exactly like this. So you have steam coming in on this side. Steam is contained within these tubes. And then you have like a really hot molten salt, and you're trying to boil the steam. So the salt comes in, and in order to get good heat transfer, you want a relatively high velocity. So they achieve that by putting these baffles in and forcing the fluid to kind of go back and forth. So you have what's called a cross-flow locally. So locally it's cross-flow, but overall it's counterflow, right? So it's a counter cross-flow design. And again, this is going to be different from a pure cross-flow, a pure counterflow. It's some mixture of the two. And then the degree to which it approaches a counterflow depends on how many baffles you have. If you have an infinite number of baffles, it's essentially a counterflow problem with a really high heat transfer coefficient on the hot side. So just another common one that you see. So what we can do with this, I guess, is do some analysis on it.